Okay, let's get started. So, last time we talked about some CPU-related background, and in today's lecture, we're going to talk about some OS-related stuff. So finally, some OS-related stuff. Okay, so the first topic that we're going to talk about is CPU virtualization. So before we get started, let me maybe... Do you know how to hide this stuff by any chance? Yeah, let me move it to the bottom. Okay. Okay. So recall that that the way that we compile the code, we first have a C program. We run the compiler, such as GCC, or maybe other compilers like Clang or Microsoft C, whatever you use, and then you run it through this. You get the assembly program. So this is typically .s file in Linux. So I should say that the assembly program is somewhat optional nowadays. So you may get an assembly, intermediate assembly, or sometimes the C program is directly compiled to a binary format. So assembly program is somewhat optional, but in the traditional way, how we compile the program is from C to assembly. Then we get the binary object file, for which we use the assembly, like GCC assembler or AS command. So we finally get an object file, and then we can use a linker to get an executable file. So we cannot yet use an object file because it still has certain things that are some unresolved symbols, some unresolved relocations, and so on. So therefore, you have to do some extra steps. So for this purpose, we use a linker. And finally, when we build an executable file, we may also need to use some static libraries, such as, for example, libc. Or we can use shared libraries also, like libc can be like a static library or as a shared library. So, for example, if you call a malloc in your program, so you would use that function from a library. So if it's a static library, it's also going to be directly linked to the executable. So now, when you load an executable, if it was a static library, that's already part of the executable. If it's not a static library, if it's a dynamic library, that's going to be connected during runtime. So this is when you launch the program. So for example, typically libc nowadays is a shared library. So you can modify libc without modifying your program. So if let's say there is some bug in a malloc or printf, which is very unlikely, but who knows, right? You can fix it in libc without recompiling your program. And finally, when you launch an executable, you launch it into memory. So and this is where it's going to be executing. So both code and data. So just to so just to kind of to kind of recap what we did in the last lecture. So we recalled some, before the last lecture, we recalled some important C topics. So also during last lecture, you had the CDB tutorial, right? And some of you have already asked me, what should I do if I have some knowledge gaps in the C language? Well, in that case, I don't have any strong recommendation, but when I was a student, actually was probably high school student. Yeah, so I read the C programming language by Dennis Ritchie. Yeah, so and if you if you want to study C language and you have some knowledge but you still have some gaps, maybe it's a good textbook, right? So again, I'm not saying that you should read this particular book. You may read something else. as long as it's a good textbook. So the only note I want to say that if you get the C programming language by Brian Kernighan and Dennis Ritchie. So by the way, Dennis Ritchie is you probably know that, right? So it's a very famous person, right? So he's like he was developing C, right? And he was also developing Unix initially, right? So and this is I think you probably have heard about him. And Brian Kernighan, of course, is also a known person. So the only thing I want to mention is that don't read the original, of course, version. Read the second edition, which is on CC, right? Because the original version of C was not standardized. It has certain differences with the with the C language that we currently use. Okay, so that's just a minor note. Any questions so far about C, about debugging? Maybe you have some questions, maybe what you need to read or whatever. Okay. So what is an OS? Well, can someone give some sort of term for this, like at least informally? Okay, go ahead.
It's like a program that manages all the other programs your computer runs.
Yes. What does it manage?
Resources.
So what kind of resources?
Shared resources.
Well, but let's be specific, right? So what kind of resources does it manage? I mean, does it manage CPU? Yes, so CPU is one resource. Okay, go ahead.
It's software that helps connect.
Well, let's kind of finish his definition. Oh, okay, yeah. So what resources?
Hardware.
Well, what specific resources, right? So CPU is one resource. What other resource?
CPU, RAM, storage.
Okay, so storage. Can you say that in more general terms, right? When you say storage. IO, right? So IO devices, right? I think that's pretty much what it is, right? So it's shares CPU, memory, IO, right? So this is what an OS is. So the first thing that we're going to talk, I mean, there is different way how you can actually define an operating system. So we kind of defined it informally. But the first task that you can say that an OS has to perform is virtualization. So it actually has to hide the hardware details, and this is probably what we also didn't mention yet in our informal definition. So when we said managing resources, so it has to hide the hardware details and provide an easy interface to programs so that they can use, like, for example, I don't want to use some IO registers when I want to print something on the screen, or I don't want to use some IO registers when I want to talk to hard disk, right? So I want to use some simple interface. I want to call some function in a library, like when I do printf or I read from some file and so on. So that's what it is. So we previously mentioned different resources. So for CPU, the virtualized resource is going to be a process or a thread. So how many of you have heard what a process or a thread is? Okay. So we'll talk about this in this course, but fundamentally it's an entity that allows you to kind of provide some sort of virtual CPU to your program, a virtual slice of your CPU to a program. So therefore, we can reasonably say it's a process, or a processor thread is a virtualized resource for CPU. I guess if you already know about this, it's kind of straightforward. If you haven't heard about it, so that will come up soon. So don't worry about this. So what is the technique that is used here? So when we share the same CPU by multiple programs, right? And when I get this, each entity gets a slice of the CPU time, right? It's effectively time sharing. So I'm time sharing the same CPU or multiple CPUs, and I'm doing context switch from one process or one thread to another process or another thread. So what is another resource? Main memory, right? So we talked about RAM. So it turns out that OS is also virtualizes this resource because each program has to have its own vision of this memory, right? So it has to kind of manage it as though the entire memory belongs to this program, right? So to say, right? So for that purpose, we use virtualized resources and address space, and the technique that we can use virtual memory. So how many of you have heard about virtual memory, page tables, or segmentation? Okay. Yeah, so virtual memory is the technique. Again, it's gonna come up in the course. So if you haven't heard about this, you'll learn it soon. So the third resource is an IO device, IO devices in general, right? Not just one device, we have many IO devices. So what is an example of virtualized resource? Well, as we mentioned, we, for example, want to work with files if we are talking about storage device. If we are talking about network device, we want to work with sockets. So there's a way to there's an abstraction that is offered by an OS. So what is the technique? Well, for file systems, we use a file system driver. For networking, we will use TCP/IP stack. Those going to be high-level stack, of course. So what we're going to use for storage and what we're going to use for the actual NIC adapter, that's also another thing, right? So we can also do some sort of virtualization at that level. But those are details. So we don't want to go to that too much right now. So again, free resources, all these free resources are virtualized. There's special techniques that OS uses to virtualize these resources. So virtualization is one task that OS is going to do. So virtualization creates an illusion that that the entire machine belongs to me, so to say, right? Whether it's a CPU, whether it's memory, whether it's an IO device, right? So I want to have that illusion in my program. So now the second problem that OS has to solve is resource allocation. So let's say you run multiple programs. How do you know how you're gonna split your CPU time failure so that all these programs are gonna take get their share to run on the CPU? How do you actually split your memory across different programs? So this is what resource allocation is. So that's another problem that OS has to resolve. So, and finally is we have to solve another problem, right? So what if a program, is doing something illegal, trying to access some memory that it's not allowed to access, or it's trying to execute some CPU instruction that doesn't exist. So we would have to have some way to control the execution of the program, right? And we have to, so that we can prevent errors or improper use of the computer. So if something bad happens, we want to probably terminate this program, print an error to a user and say this program is buggy or whatever, right? So please tell the developer about this. I don't know, Windows throws this error sometimes, right? Or used to throw this error. And in Linux, you will get segmentation fault or something similar. Any questions so far? Okay.
So the first thing that we want to look at, and by the way, if I highly recommend, especially those of you who haven't heard about processes, threads, and other concepts that we are going to discuss, I highly recommend you to look at the OS Free Easy Pieces textbook that we have. So please check that textbook. It's very useful. And specifically, we have some material today that is already covered by one chapter. So we are not going to go from one chapter to another chapter. So we are not going to go in the same order, because they have one rationale why they use that order. We shouldn't follow the same order. So you don't be surprised if you see like chapter 13, then chapter 6 and something like this. So it's not going to be it's going to be completely different order. But please check chapter 13 and section 3. So I'm going to also put some references to syllabus. So whenever we have some lectures, I'm going to post, please read this chapter from textbook and so on. So a process is a fundamental OS abstraction that we have. So it's effectively creates some sort of virtual machine by the OS, but virtual machine not in the sense that you use virtual machine to run operating systems, but virtual machine in terms of running some particular program. By the way, those concepts are not entirely different, but they're different, right? So, but they are not maybe they're different from practical implementation, and they're different from whatever techniques the CPU offers. But from theoretical sense, there is some actual similarity there, right? So when I say it's not the same virtual machine, I mean the only difference that you run the entire OS versus a separate program, right? From the theoretical standpoint. But of course, from the implementation standpoint, it's going to be entirely different. So a process is basically creates this sort of virtual machine. So, I believe that you should have covered processes if I if I know correctly, right? That this is pre-11 and preceding courses. So please revise it. So it seems like not all of you remember what a process is, but please revise it. So you may not necessarily know things like page tables, right? So those we will cover, but I think certain basic concept you should have covered in the prior courses. Yeah, so please revise what the processes are in general, right? So I'm just giving a very general definition, but just please revise what it is, right? And you also revise how to get information about processes on your computer. So for example, when you run Linux, how can you use the top utility, how you can use the proc file system. At least some of this is useful to know. If you have never tried to deal with this, you can also look at the man page, man pages in Linux, manual pages, right? So you can always type man proc and see documentation for that. Or man top or man proc or whatever it is, right? So whatever you are interested. So, but in general, you probably have seen Task Manager, whether it's in Windows or Linux, or when you can terminate some programs, right? And more specifically, you can terminate processes. So, so for processes, please take a look. So especially if you don't know what, or don't remember what process is, or have some gaps, please take a look at chapter 5 of OS 3 Easy Pieces. So that should help you. And just to just recall that the API that we use is fundamentally just several functions. The most important one is fork. So fork clones the current process and creates a new process. So it's basically initially it's the same. It's basically a clone initially, but after some time, these processes can diverge. So that's the general idea. So whenever you want to launch a new program effectively in Linux, the way that it works, you first create a clone of the previous program. So it's actually done very efficiently. So you may wonder why I need to create a clone, right? If I'm not going to run it. Well, it turns out that it's actually done very efficiently. So you don't need to worry about this. But the idea is that you create a clone of the current process, and then you're going to substitute whatever you were running with something else. So how do you substitute? You use the execv function. So execv transforms current process to a specified program. So the specified program is in a separate executable file. And in that executable file, you have a new code that you want to execute. So initially, the idea is that, let's say you are running your bash command, right? So you run in terminal and bash, right? And you want to run some command. So the first step that bash will do, it will create a clone of itself, right? So it's going to run fork. So the second step, the original parent process will continue execution like a previous process, right? So it won't change. But the new process will substitute code from the new executable file, which is going to come from execv. Again, you may wonder, why is it like this? Why, if I'm going to substitute it anyway, why do I need to run that kind of complicated? Why do I need to create a clone and then change it, right? So it sounds kind of, unnecessary. So the way it's done, I mean, I don't want to go too much into details, but the way it's done, it's kind of copy and write technique. So unless you are modifying this process, you are not gonna pay any penalty, right? So you're not gonna be duplicating memory, or you're not gonna do anything like this. In case if you are curious, right? But in case if you are curious, if it's a good interface or bad interface, I think it's a bad interface, but it's unfortunately what it is, right? So I think there are some even security issues with this. Nowadays, there's some security papers which argue that fork should not be used. But fork is used historically, and that's what it is, right? So unless we want to rewrite all existing programs, it can be a little bit hard. Yeah. So my personal opinion, it's probably not the best interface, but that's the way that original Unix came up with, right? So that's the original idea. So exit terminates process with some exit status. So let's say you in your program you're trying to open a file, the file doesn't exist, and you want to just terminate your program, just print some error. So so you want to exit. So you can call exit and just immediately terminate the program. So, and finally, the other call is wait. So as I previously said, that there is some sort of parent process and then there is a child process. So in the parent process, sometimes you want to wait while the other process completes, right? So you have a special call for that, right? So for example, bash, if we come back to the bash example, remember when you run a program, it doesn't print the command prompt until this program completes. So it effectively waits until this program completes. So this is what can be achieved by the wait call. Any questions? So how many of you have seen that before? Fork, exec. Have you used it? Oh. Yes, I kind of have you used it in 3.11? A little bit, right? Okay. Yeah, so again, if you I mean, I know you come from different like years and so on, right? So like some of you have taken 3.11 one semester, and other students different semester. There might be some differences in program. So in case if you have some gaps in this, I highly recommend you to read the textbook, and probably it's worthwhile to read it anyway, just to even if you remember what it is, because you might find some interesting details which you have not been aware of before. So like, please take a look. If you find that, I don't learn anything by reading this textbook, I already know that information, that's fine, right? But But otherwise, please take a look. Okay. So let's come back to a process, right? And the process definition. So process is actually a bundle of resources, because it's not just CPU time that we want to manage, and it's not just some sort of it's just one aspect. I want to give a slice of CPU time for this program to execute. But another thing is, of course, I want to create a separate address space for this program. So another resource that a process is going to virtualize is a address space. So also a variety of different information. Remember, we talked about IO device virtualization. It turns out that process also provides some mechanisms for IO virtualization. It keeps a variety of different information. So for example, it will keep what kind of file descriptor you have opened, what kind of files this particular program or process, right? So I'm gonna use program in case if you're still not sure what the process is, right? But there's a difference between a program and process. So the difference is that a program may have multiple processes, right? So potentially. But in simple case, it's just one process. So a process will have a variety of different information, file descriptors, pipes, network sockets, or whether you have like file system open, or whether you have some socket of a network socket open. So it's going to be a file descriptor. Then it's a process ID, right? So that's like when you want to terminate a process, you run kill command in the terminal, right? So for that you need the process ID. So if you know the process ID, you can terminate the program. So process state, whether it's running, blocked. So we will talk also about scheduling. When we talk about scheduling, we'll talk about different states of processes. So as I said, processes in a simple case, your program or application will have just one process, but in more general case, it may have multiple processes. So what would be an example of multiple processes in a single application? Any ideas? I'm pretty sure you have used that. Many of you have used that application. I'm pretty sure almost everyone uses it, right? So any clue? Yes, like a browser, right? So you run a browser, and as far as I know, each tab will be in a separate process, right? So for security reason, they run it in a separate process because you're gonna have your own, so to say, virtual machine or their own address space, own resources and so on, for exactly the same reason, right? You want to isolate one tab from another tab completely, right? So that it doesn't. Nothing malicious. Like if it's some malicious page, it doesn't do anything bad to another page. Yeah. So that's the idea. If you have one tab open your bank account, right? So another tab some shady website. It's a good idea to run them in separate processes at the very least. Some security people will even run it in separate ways. So they would run a separate VM with the entire OS for that. But at the very least, you want to use the process. Okay. So let's recall what a process address space is. Again, if you if you have missed that for some reason, you can revise that in the textbook. The textbook also have a pretty good description. I'll just gonna have some general idea. So recall what basically an address space is. So you have a set of so you have basically addresses, right? So if we're going from 0 to maximum address. So in this example, we're going to go from 0 to 4 gigabyte. Nowadays, when we deal with 64 bit architectures, we are not limited by 4 GB. The limit is much higher, even though it's not 2 to the power of 64 actually, but it's still a little less, but it's still very big, right? It's not 4 GB anymore. So fundamentally, you can view that as an array of bytes. So memory, so the minimum unit that you cannot you access in the memory is a byte, right? So you can view it as some sort of bytes. And you know, different parts of virtual memory going to hold different parts of your program. So for example, you know, maybe in the beginning you're going to put code of your program, then later you're going to put a data section from your executable file, so where your global data is resided. So then maybe you have some dynamically allocated memory. You're going to have a heap. And you know, so that you're going to be yet another virtual address space range. So, and you also have stack, right? So you also, whenever you want to call a function, you want to, at the very least, to keep a return address on that stack so that you can go back to the original function. So at least gonna have a chain of return addresses as you call more and more functions. So also, if you have some local variables in each function, like you know, or some array, like local arrays. Again, if it's not a global data, if it's local to that function, that's going to reside on stack. So in this example, we call main, then we call foo, and then we call bar. So also, one thing to keep in mind here is that yeah, something I wanted to tell. Just give me 1 second. Yeah. So also the way that, I mean, it doesn't have to be like this, but also it typically puts stack on the, at least on x86 64 for certainly, right? You put stack on the opposite kind of side of virtual memory, or at the very least in some distinct side of virtual memory. So you see that you don't know in advance how large heap is going to get. All right, so how large heap is going to grow, right? So maybe initially it's just 1 megabyte, but later you want to use 1 gigabyte, you know, 2 gigabytes, 4 gigabytes. And the same for stack. You know, you don't know in advance how many functions you're going to call, how deep your stack is going to be. So it's kind of good to put them into the opposite sides. So the stack goes, so the stack going to grow in a different direction. So heap or whatever core data you have, that's going to be some sort of normal direction from a lower address to a high address. And for stack is going to be from high address to a low address. So that's exactly what this picture shows, right? So you have some free space in between, but you don't need to know in advance how much space you will need. So also recall one thing, that when I say that it's an array of bytes and virtual memory is sort of array of bytes, it doesn't necessarily mean that we will have to allocate memory for that, right? So for example, for this white space that we have, we don't need to have any physical memory for that, right? So so it can be just empty space. So, and the actual techniques, how we do that for page tables, we will describe later in the course. But again, virtual address space doesn't always have to be substantiated by real memory, right? So, or it can, sometimes virtual memory can also work such that you keep certain data on your storage device and then bring it back, you know, so all kind of combinations are possible. So you don't always have to keep it in RAM. Okay, so also recall that there are some special registers. I mean, there is general registers, general purpose registers that we have in a CPU, but there is also special registers. One of this register is called a program counter. So it's not a typical register that you can write or read to. Well, sometimes nowadays they're allowed to read from program counter, but in general it doesn't have to allow that. But it's not something that you temporarily store your data, right? So it's a special register. So it's special register which will, depending on the architecture, it will either point to the current instruction or to the next instruction. So again, it depends on the architecture because for x86 it's going to be the current instruction. But in general, right, like traditional computer science program counter, that would be next instruction. But the reason why x86 is doing it because your current instruction can be of variable size. So if you have fixed size instruction, then there is no problem. Like RISC architectures have fixed size instructions, so it shouldn't be a problem there. So anyway, it's a minor detail. So it's either the current instruction or the next instruction. So stack pointer SP, it's going to be address of the top of the stack. So like we talked about here, like bar, full bar, main, right? So initially it's just main. So your stack pointer should point to main. So once you call full, your stack pointer going to get updated. Once you call bar, your stack pointer is going to be updated even further. So for x86-64, stack point is RSP. For an instruction pointer or program counter is RIP. So for 32-bit, it's EIP or an ESP correspondingly. So it's just it's just a piece of this register. So that's just a piece of 32-bit piece of this register, effectively, right? So the only difference is that they have expanded this register to 64 bits. They made it larger. Okay. Any questions so far? Yeah, I'm pretty sure some of you have some questions. Any questions? Don't be shy. Okay. So how many of you remember these things like about virtual address space, program count, and stack pointer? Okay. So what course was this? Was it 331 or 311? Which one? I'm sorry?
330. 331.
Okay, 331. Okay. So again, so whenever we call function, you're going to create a frame, and whenever you're going to return, you're going to go to the opposite direction. So now you're going to erase the frame. So you're going to erase bar, then you're going to erase full, you're going to erase min. So by erasing, I mean just adjusting stack pointer. So it's just, you don't need to do anything with memory unless you want to be, unless you have some strict security requirements to zero out that memory, you don't want to do that. So what does the stack frame contain, right? So return address is one thing that we certainly have to keep because this is where we need to know the place where we want to come back to. Function local variables and also arguments passed to the function. So typically nowadays for x86-64, your first 6 arguments are passed through registers. So if you use 6 arguments, typically you won't need to pass arguments through stack. But if you have a function which has too many parameters, right? Like at least 7 parameters or maybe 8 parameters, that will go to stack. Also for Windows, the calling convention is slightly different. So I think for the first 4 parameters will be passed through registers. If you have 5 parameters, that will already use stack. So, so if a process uses shared library, we still have this white space in between, so we can map this shared libraries in that place. So what is a shared library? Well, I gave an example of a shared library as libc, right? The libc is a special library where we have malloc, free, printf, all this kind of function that you use in the C language. And guess what? Almost all programs want to use it, right? So do you want to replicate this code? Probably not, right? So you want to just create one binary. It's not just one binary that you want to compile, but ideally, when you execute this binary, you also don't want to replicate it in memory. Because what's the point of replicating the same code in memory? You may need to, in case of shared libraries, you may still need to modify to replicate data, because especially if this data is modified by each process independently. So perhaps for data you have to duplicate it, unless it's read-only data, like such as strings and whatever you print, some messages that your library contains, like whatever you put as const char star, right? So that will be strings. Typically they will put it in read-only memory. But aside from that, code is also read-only memory, right? So this is not something that a program will modify. So that parts you can actually share across different processes and across different programs. Okay, go ahead.
How do we know where between the stack and the heap we put the shared libraries if we don't know how big either of them are going to be?
Yeah, so it's a good question. And, the question is actually even more interesting because nowadays we have randomization, address-based randomization. So that means you will deliberately choose a completely random address. So I guess you have some limit for your stack, right? So you know how what's the largest possible stack? I think it's like 2 megabytes, or like, I don't know what's the default now, but I think it's probably more than 2 megabytes nowadays. So it's going to be some limit, but it's going to be a reasonable limit. It's not going to be like, terabytes or something like this, right? So it's going to be a quite reasonable limit. So you know that the point you will kind of reserve that space. And the same as for heap, you can also define what's your largest heap size, right? So that can be also a parameter in the operating system, because it also doesn't want to allow infinite amount of memory. So those things you can control for each program. And I guess it's a less of a concern for 64-bit programs, because the address space is so gigantic, you don't have so much memory in your computer, right? So clearly you will always have sufficient virtual address space. Now for 32-bit processes where you only have 4 gigabytes of memory, and if you run some heavy applications such as Chrome browser, perhaps, so perhaps it's not going to be great, right? So it's going to you have to you have to decide, right? So you have really tight constraints. Yeah, so there's no good answer, but there's no, I should say there is no a completely definite answer, right? Because it depends whether it's a 32-bit architecture, 64-bit architecture. And for 32 bits, we are more constrained. For 64-bit, we can just assume whatever limits for stacks and heaps are, they're reasonable, and we will always have space in between. Now, the other thing I mentioned, you want to randomize. Sometimes you want deliberately, for security reasons, pick a random address. You want to pick a random address for heap. You want to pick a random address for stack. You want to pick a random address for shared libraries, so that an attacker doesn't know where these things are located in your program. Does it make sense?
Yes, thank you.
Okay. So with ASLR, this is exactly what I mentioned right now, right? One thing that you can do, you can run randomized locations. So you can use so-called position-independent code. So in position-independent code is based on the instruction pointer addresses. So all addresses become relative to instruction pointers. So if you have some global variable, that can be relative to the instruction pointer. If you have some function call, that's going to be relative to the instruction pointer, and so on. So by the way, lecture is at 10:20 or 10:10? 20, right? Okay, just want to double check that. Okay, so you know, for that reason, if you want to randomize, you can use position independent code. That's already used for shared libraries for x86-64 because why? So any ideas why do we want to do that for shared libraries? Any ideas? Because the same code will have to be executed in address space of another space of one program and then another space of another program. But we don't know in advance how many shared libraries are going to be used by one program and by the other program. Let's even put aside SLR stuff, right? So we'll just consider that we don't need to randomize anything. We just can run at some fixed location. But the problem is maybe one program is using libc and libp thread, but the other program is just using libc. And can you make easy assumptions where you're going to load the shared library? Or maybe this you have some you know, another library shipped by some third party, and that unfortunately occupies the same space which was reserved for libp thread, right? So therefore, there is no good way to manage this memory in advance. And ideally, what you want to have a position independent code so that at runtime you can choose whatever address you like. So if you like that address, the code will still run. If you like another address, that will also run. So this is exactly what you can do with position independent code. So in position independent code, addresses are going to be relative to the instruction pointer. Okay. You know, so for just before we probably gonna wrap up in a second because I wanna probably stop here. You know, again, you can have multiple processes like processor A and process B. They may have running different programs. Like for example, first program is running main, foo, and bar. Maybe the other is called main, func, and so on, right? So that's completely different code. It's got its own heap. It's got its own data. It has its own code. You know, sometimes some pieces can be shared if you use shared libraries. So, for example, code from shared libraries can be shared. But generally speaking, processes will run, you know, entirely different stacks, entirely different heaps, entirely different code and data, right? So in general. Okay, yeah. So any questions about this, right? Is it clear that mechanism? Okay, so we'll go into much more detail soon about virtual memory, but just for a moment, assume that there is some mechanism which you can use to effectively create a virtual address and map it to a physical address, right? So whatever program thinks an address is whatever the actual physical RAM address is. So there's a way to translate these addresses, and there is a way to allocate physical addresses for a virtual address space. Okay, let's stop here because that's next time we'll start a different topic. So I will upload the slides, I guess, today, yeah, after the lectures.